Right now, Earth is spinning faster than it has in decades. Then, this year, it started slowing down again. A hole in our planet's shield is stretching wider every year. A giant ocean current that keeps a whole continent from freezing is losing power. Space rocks are hitting us from angles that should not exist. Something is shifting deep in the ground, deep in the ocean, deep in the sky. If you enjoy uncovering what is really happening to our planet, hit like and subscribe before we go further. Every fact ahead is real, checked, and stranger than fiction. Get ready. Earth is changing right in front of us. Go outside tonight, find the brightest star you can, and look straight at it. Something remarkable is happening in that moment. The light landing in your eye is old, older than your grandparents, older, in some cases, than the pyramids. It began its journey long before you were born, crossed an ocean of empty space, and finished the trip inside your eye tonight. Take a star like Betelgeuse, the reddish shoulder of the constellation Orion. It sits about 640 light-years away. That means the light you catch from it left the star around the time of the late Middle Ages, when knights still rode across Europe. The star could have exploded 200 years ago, and you would have no way of knowing. The news simply has not arrived yet. You are looking at a portrait of the past, painted in light, delivered late. This is the strange gift of the night sky. Every point of light above you is a message sent across time. The farther away the star, the older the message. Some of the faint smudges you can see are entire galaxies, and their light has been traveling for millions of years. When it finally reaches you, it is showing you those galaxies as they looked before human beings existed. Now, here is the part that should stop you cold. All of that light has been traveling for centuries, for thousands of years, for millions of years. It has crossed distances so vast that our fastest spacecraft would need longer than the age of the Earth to cover them. And yet the light itself has not aged a single second on the journey. It arrives exactly as fresh as the instant it was born. Think about what that means. If you could somehow ride along with a beam of starlight, carrying a stopwatch, you would press start at the moment the light left the star. You would fly across 600 years of space. You would arrive at the Earth, and your stopwatch would still read 0. No time would have passed for you at all. The centuries that ticked by for everyone else would mean nothing to the light. For the light, leaving and arriving happen in the same breath. That sounds like a magic trick. It comes straight out of the most tested theory in all of physics, the work Albert Einstein published more than a century ago. His equations do more than allow this. They demand it. The universe is built in such a way that light, and only light, gets to skip the passage of time entirely. How can something travel across the galaxy and never grow older? How can a beam that spends 1,000,000 years crossing space experience none of it? The answer forces us to throw away almost everything we assume about time and distance, and to see them the way the universe truly works rather than the way they feel to us. To understand why light never ages, we first have to understand why light is so special in the first place. Because before we can explain its frozen clock, we have to explain the one thing light can never do, no matter how hard the universe pushes it. And that single limit is where the whole mystery begins. Light has a speed limit stitched into its very nature, and the rule works in a way that feels almost unfair. Light must travel at one exact speed. It can never go faster. Stranger still, it can never go slower either. In empty space, light always moves at roughly 186,000 miles every second. Always. That is fast enough to circle the entire Earth about 7.5 times in the time it takes you to blink. Why is light locked to that one speed? The answer comes down to a single property. Light has no mass. A particle of light, called a photon, is a bundle of pure energy with no weight to it at all. And in our universe, anything with 0 mass is required by the laws of physics to move at exactly that speed. It has no choice in the matter. To feel why, picture the difference between throwing a bowling ball and shining a flashlight. The bowling ball has mass. To get it moving, you have to shove it. and the harder you want it to fly, the more effort you must pour in. Give it a gentle push and it rolls slowly. Give it everything you have and it flies faster, though there is always a limit to how fast your muscles can hurl it. Mass resists motion. Mass is the thing that makes speeding up hard work. Now imagine an object with no mass at all. There is nothing to resist. There is no heaviness to overcome, no sluggishness to fight. The instant such a thing exists, it is already moving at the maximum speed the universe permits. A photon is born running at full speed and stays there for its entire life. It runs at the top speed from birth, and it holds that speed because there is nothing in it to slow. This leads to one of the deepest divides in all of nature. Everything in the universe falls into one of two families. Things with mass, like you, planets, bowling balls, and stars, are forced to move slower than light, always. And things without mass, like photons, are forced to move exactly at light speed, always. There is one clean line between them, with no middle ground and no crossing over. A massive object can be pushed closer and closer to light speed, yet it can never quite reach it. A massless object can only ever travel at that one speed. Here is a number to hold on to. To push even a single speck of dust all the way up to light speed, you would need an infinite amount of energy. Not a huge amount, infinite. More energy than exists in the entire universe. That is the wall that mass builds, and light sails past it effortlessly because it carries no mass to begin with. So light is special from the very start. It lives in the fast lane that nothing heavy can ever enter. It is the universe's ultimate courier, sprinting across the cosmos at the one speed reality allows, and refusing to slow for anything. But this raises a puzzle that troubled physicists for years. If light always moves at that fixed speed, then what happens when you chase after it? What if you climb into the fastest rocket ever built and race alongside a beam of light? Surely, if you move fast enough, the light should appear to slow down beside you. The answer to that simple question broke physics wide open. Imagine you climb aboard the fastest spaceship ever dreamed of and chase a beam of light across the sky. Every instinct you have says the light should slow down relative to you. If a car passes you on the road at 70 miles an hour and you speed up to 60, the gap between you shrinks, and the other car seems to crawl ahead at only 10 miles an hour. Speed up enough, and you pull alongside it. That is how motion works in daily life. Chase something fast enough, and it appears to slow. So you fire your engines and race after a passing beam of light. You reach half the speed of light, then 90%, then 99%, screaming through space, faster than anything humans have ever built. Surely now, the light beside you has slowed to a gentle glide. You look over, expecting to see it barely creeping ahead, and the light is still pulling away from you at the full speed of light. It holds the exact same speed it had before you ever left the ground. You could push to 99.99% of light speed, pouring in unimaginable energy, and the beam beside you would still race ahead at precisely 186,000 miles per second, as if you were standing perfectly still. This is the fact that shattered the old picture of reality. The speed of light is the same for everyone, no matter how they move. A person standing on the ground measures it. A pilot streaking through space measures it. A photon fired from a galaxy rushing away from us measures it. They all get the identical number. Speed of light in, speed of light out, always the same. Young Albert Einstein took this bizarre truth seriously when almost no one else would. Other scientists tried to explain it away, inventing invisible substances to fill space and hide the problem. Einstein did something braver. He accepted the measurement exactly as it was and asked what the universe would have to be like for it to be true. His conclusion sounds impossible at first. If everyone always measures light at the same speed, no matter how fast they themselves are moving, then something else has to give. Speed is just distance divided by time. If the speed refuses to change while your motion changes, then distance and time themselves must be bending to keep the answer fixed. Picture speed as the result of a seesaw between distance and time. In everyday life, we assume the seesaw sits still, that a mile is always a mile and a second is always a second for everyone. Einstein realized the seesaw tilts. To keep light's speed nailed to one value for every observer in the universe, space has to stretch or shrink, and time has to speed up or slow down, depending on how fast you travel. That single idea rewired our understanding of everything. Time became flexible instead of a steady drumbeat ticking the same for all. Distance became flexible instead of a fixed ruler everyone shared. Both bend quietly in the background to protect the one thing the universe holds sacred, the speed of light. And once time itself can stretch and slow, a haunting question appears. If moving fast enough slows your clock down, then how slow can a clock go? Push closer and closer to light speed, and what finally happens to time itself? There is a clock on the wall, a clock on your wrist, and a clock ticking quietly inside every cell of your body. And Einstein discovered that none of them run at a fixed rate. How fast a clock ticks depends on how fast it moves. Speed up and time slows down. This effect has a name. Physicists call it time dilation, and it is one of the strangest truths ever confirmed by experiment. Here is the plain version. If you move faster than someone else, your clock ticks slower than theirs. From their point of view, the clock keeps perfect time. Time itself is simply passing more slowly for you. Every process that measures time slows down together. Your watch, your heartbeat, your thoughts, the aging of your skin, all of it stretches out and drags behind. At the speeds we live our lives, this effect is far too tiny to notice. Walking, driving, even flying in a jet, you gain only the faintest sliver of slowed time, far less than a blink across an entire lifetime. That is why nobody stumbled onto this for thousands of years. The universe hides the effect completely until you approach truly enormous speeds. But the effect is real, and we have measured it directly. Scientists once flew extremely precise atomic clocks around the world on ordinary passenger jets, then compared them to identical clocks left sitting on the ground. When the planes landed, the flying clocks had ticked slightly less than the ones that stayed home. The difference came to mere billionths of a second, yet it matched Einstein's prediction exactly. Time really had slowed for the clocks in motion. You depend on this effect every single day without knowing it. The satellites that run the location system in your phone orbit high above the Earth, racing around the planet at thousands of miles per hour. Their onboard clocks tick at a slightly different rate than clocks on the ground, and engineers must correct for it constantly. If they ignored the slowing of time, your maps would drift off by miles within a day. Every time your phone shows where you are, it is quietly accounting for the fact that time bends with speed. To picture why this happens, imagine light bouncing straight up and down between two mirrors, like a ball bouncing between a floor and a ceiling. Sitting still, the light travels a simple up and down path, tick after tick. Now set those mirrors moving sideways at high speed. From the outside, the bouncing light no longer travels straight up and down. It traces a long zigzag, a stretched V shape, because the mirrors slide sideways between each bounce. The light has to cover a longer path to complete a single tick, and light always moves at one fixed speed. It cannot hurry to make up for the longer path, so each tick simply takes more time. The faster the mirrors move, the longer the zigzag, and the slower the ticking becomes. That is time dilation in its purest form. Motion stretches the path that light must travel inside every clock, and every clock includes the atoms of your own body. The faster you go, the more dramatic the slowdown grows. At everyday speeds, it hides in billionths of a second. The closer you creep toward the speed of light, the more violently time drags. The question is how violent it can get, and there is a single number that measures exactly how much time bends at any speed, a number that stays gentle for most of the journey and then does something explosive. Every effect in Einstein's theory of motion flows through a single number, and that number hides a shock inside it. Physicists call it the Lorentz factor, though you can simply think of it as the stretch factor. It tells you exactly how much time slows down and how much distance shrinks at any given speed. For most of the range, it behaves politely. Near the end, it goes berserk. Here is how the stretch factor grows. When you sit still, it equals 1, meaning time runs normally, with no stretching at all. As you begin to move, it inches upwards so slightly you would never notice. Even at a large fraction of light speed, it stays surprisingly calm. Then, as you close in on light speed itself, it stops climbing gently and rockets toward the sky. Look at the actual numbers, and the pattern is unforgettable. At 90% of the speed of light, the stretch factor sits at about 2.3. That means time runs at less than half its normal rate, pushed to 99%, and the factor climbs to roughly 7. Now time crawls at about 1/7 of its usual pace. Go to 99.9%, just a whisker faster, and the factor leaps to around 22. Each tiny step closer to light speed produces a wildly bigger slowdown than the last. This is the key to the whole mystery. The stretch factor climbs along a curve. It bends upward, then rears almost straight vertical, sending the number toward the sky. The first 90% of the way to light speed barely bothers it. The final sliver of a percent sends it screaming toward infinity. Picture a car with a very strange speedometer. From 0 up to highway speed, the needle behaves as expected. But near the very top of the dial, the markings bunch together insanely. Nudging the accelerator, the tiniest bit sends the needle flying across enormous jumps. That is what the approach to light speed feels like in Einstein's universe. The closer you get, the more every scrap of extra speed costs, and the more savagely time stretches in return. Now follow the logic all the way to its end. What happens to the stretch factor at exactly the speed of light? The math gives a clear and staggering answer. The factor becomes infinite, infinitely large, and an infinite stretch factor means time slows to a total halt. It stops. This is why nothing with mass can ever reach light speed. An infinite stretch factor would require infinite energy to achieve, which the universe cannot supply. A bowling ball, a spaceship, a single atom, all of them hit that impossible wall and can only approach it, never touch it. They stay forever locked below the speed of light, with their clocks slowed but still ticking. Light meets no such wall. Light already travels at exactly the speed where the stretch factor blows up to infinity. Light lives permanently at the edge that everything else can only dream of reaching. And that means something extraordinary happens to the passage of time for light itself, something that turns a beam crossing the galaxy into the strangest traveler in all of physics. To see it, we have to ask what a clock would read if it could somehow ride the light. Take everything we have learned and aim it at a single impossible traveler, the light itself. We know that moving faster slows your clock. We know the slowdown grows monstrously as you near light speed. So follow that trend all the way to its final destination and ask the ultimate question. What happens to time for something moving at exactly the speed of light? The math does not flinch. At the speed of light, the stretch factor becomes infinite, and an infinite stretch of time means one thing only: time stops. For a beam of light, the clock freezes solid. Every tick stops. The hands hold still. Time, for light, refuses to flow at all. Sit with how radical this is. A photon leaves a distant star. It flies across the black gulf of space for 1,000 years by our reckoning. It slams into a telescope on Earth. And in all of that time, from the light's own frozen clock, absolutely nothing has happened. The departure and the arrival are the same event to the light. What we count as 1,000 lonely years crossing the dark, the light lives as a single instant with no duration at all. To grasp how strange this is, compare a photon to an ordinary traveler. Suppose you fly across the country. You board a plane, you sit for hours, you watch the map crawl, you land tired and older by an afternoon. Time passed for you. You felt every minute of it. Now shrink that afternoon towards 0. Imagine a journey so extreme that no time passes for the traveler at all, where stepping onto the plane and stepping off happen in the very same heartbeat. even though the plane crossed the entire continent in between. That is the life of a photon, taken to a scale that dwarfs any continent. This is why we say light never ages. Aging is the passage of time doing its work. Your body ages because seconds pile up inside it, one after another, wearing you down. A photon has no seconds piling up. Its personal clock is stuck at zero forever. A beam of light born in the first blaze of a star and caught by your eye tonight is exactly as young as it was the instant it was created. It has crossed unimaginable distance and gained not one moment of age. There is a number that makes this land with full force. The light from the most distant galaxies we can see has been traveling for more than 13 billion years, longer than the Earth and Sun have even existed. Yet that ancient light has aged, on its own clock, by exactly zero. It arrives as fresh and new as the moment it left, carrying a snapshot of the young universe frozen perfectly in place across an ocean of time. So, light is a traveler for whom the journey takes no time, a courier that never grows old, a messenger unaffected by the eons it crosses. If no time passes for the light, then in a real sense the light took no journey at all. The star that flung it into space and the eye that finally catches it are, from the light's own point of view, pressed together with nothing between them. And that single idea leads somewhere stranger still. Here is a thought that sounds like nonsense until you follow the physics, and then it refuses to let you go. From the point of view of light, the journey never happens. Space is never crossed. Time never passes. The moment the light is born and the moment it is absorbed are, for the light, the exact same moment. Beginning and end collapse into one. Think about what that does to the idea of a trip. When you drive to another city, the trip is made of 1,000 in-between moments. You pass mile markers, you watch towns slide by, you feel the hours accumulate. The journey is the middle, the stretch of experience between leaving and arriving. For light, that middle vanishes entirely. There is a start, there is a finish, and they are welded together with no gap between them, no middle at all. This means something almost unbelievable about the star you looked at earlier. When a photon leaves the glowing surface of that star and lands in your eye, those two events, separated by centuries and by staggering distance in our world, touch directly in the world of the light. The surface of the star and the back of your eye are, from the photon's frozen perspective, pressed against each other. To the light, the star and your eye register as a single point of contact. Picture a vast sheet of paper with a dot on the left edge for the star and a dot on the right edge for your eye. In our everyday view, those dots sit far apart, and light must crawl across the whole page to get from one to the other. Now fold the paper so the two dots lie exactly on top of each other. That fold is what light experiences. The two dots that seemed so far apart now share the very same spot, and the light passes between them with nothing in between. This is why physicists sometimes say a photon connects its birth and its death as one unified event. In the grand map of space and time, the light traces a path that has zero length by its own reckoning. Everything along that path, every star and cloud of gas it might pass, exists for the light in the same single instant. The whole trip, however long it looks to us, is one flash with no inside, and this reshapes how we should think about the night sky above us. When ancient light from a distant galaxy finally reaches a telescope, that galaxy reaches the instrument directly through the light, stretching across billions of years to make contact in a single, timeless instant. The light is a bridge, with no length, joining the deep past to the present moment, as though they were neighbors standing side by side. It is a dizzying idea, and it can feel too abstract to trust. Light stays forever beyond our reach as passengers, so to make the strangeness concrete, physicists lean on a famous story, one that starts with something we can actually picture. Two twins, one who stays home, and one who leaves on a journey so fast that when they meet again, one of them has barely aged at all. Meet two twin sisters, born minutes apart, identical in every way. Call one the Traveler and one the Homebody. The Traveler climbs into a spaceship capable of reaching nearly the speed of light. The Homebody stays on Earth, waves goodbye, and settles in to wait. What happens when they meet again is one of the most famous and unsettling results in all of physics. The Traveler blasts off and races out into space at 99% of the speed of light. She flies for what feels to her like a short trip, a few years at most. She reaches a distant star, loops around, and comes home. She steps off the ship, barely older, still young, still vibrant. Then she looks for her sister. Her twin is an old woman. While the Traveler aged only a handful of years, decades poured past on Earth. The Homebody lived through grey hair and wrinkles and a lifetime of birthdays, while the Traveler skipped almost all of it. They were born at the same instant, and now one is young and one is old. The clock on the spaceship ran slow, exactly as the stretch factor demands, and slow clocks mean slow aging. This has stopped being pure theory. We have never sent a person on such a trip, yet nature performs a smaller version of it constantly. Tiny particles called muons rain down through the atmosphere at nearly the speed of light. Left on their own, muons fall apart in a fraction of a heartbeat, far too quickly to reach the ground, yet they arrive at the surface in huge numbers. Their internal clocks run so slow at such speeds that their brief lives stretch out long enough to complete the trip. They are the traveling twin in miniature, surviving because time slowed for them. Now push the twin story to its ultimate limit. The faster the Traveler flies, the younger she is when she returns, and the wider the gap between the sisters grows. Take her all the way to the speed of light itself, the speed at which the stretch factor becomes infinite. At that point, she would age by nothing at all. She could cross the entire galaxy and come back in what feels to her like a single instant, while millions of years swept across the Earth she left behind. That impossible endpoint, the Traveler who ages by exactly zero, is precisely where light lives. Light is the twin who takes the journey to its absolute extreme. Every beam of light is a Traveler moving at the one speed where aging stops completely. It leaves, it crosses the cosmos, it arrives, all of it happening with no age gained at all. The twin paradox, stretched to its breaking point, becomes the everyday life of a photon. To imagine it, picture the traveling twin flying faster and faster, her clock ticking slower and slower, her face aging less and less with every gain in speed. Push that dial all the way to the end, and her clock stops mid-tick and holds there forever. That frozen clock is what every ray of sunlight carries as it falls on your skin. So, time bends brutally for anything approaching light speed. Yet time is only half of what the Traveler experiences, because when the twin looks out her window at the star she is racing toward, she notices something else has changed, something about the distance itself. The space ahead of her has begun to shrink. The traveling twin, racing toward a distant star at nearly the speed of light, glances out her window and sees something bend that she always trusted to hold still. The distance ahead of her has shrunk. The gap between her ship and the star she is chasing has grown shorter than it had any right to be. Space itself, in the direction she is flying, has squeezed. This is the twin of time dilation, and it carries its own strange name. Physicists call it length contraction. The rule is simple to state. When an object moves very fast, the space in front of it, measured along its line of travel, shrinks. The faster it goes, the more the distance collapses. It only happens along the direction of motion. A fast-moving ruler pointed the way it travels gets shorter. That same ruler turned sideways stays its normal length. So, a spaceship screaming through the cosmos would appear squashed from front to back while keeping its full width, like a photograph pinched thin from the sides. And the shrinking follows the very same explosive pattern we saw before. At 90% of light speed, distances collapse to less than half their usual size. At 99%, they shrink to about 1/7. At 99.9%, a stretch of space folds down to roughly 1/22nd of what someone standing still would measure. The same stretch factor that slows time also crushes distance, step for step, in perfect lockstep. Here is why this must be true. The traveling twin and her sister at home have to agree on one thing: the speed of light. Speed is distance divided by time. The twin's clock runs slow, so time is stretched out for her. If distance stayed normal while her time stretched, the two sisters would calculate different speeds for light, and that is forbidden. The universe fixes the problem by shrinking distance for the traveler by exactly the amount needed to keep light speed identical for both of them. Time stretches, space squeezes, and the speed of light stays nailed in place. You can feel the logic in the muon story from before. Those tiny particles rain down through miles of atmosphere and reach the ground even though they should decay almost instantly. From our view on the surface, they survive because their clocks run slow. From the muon's own view, its clock runs normally, but the atmosphere it must cross has shrunk to a thin sliver. Both descriptions give the same result: a muon arriving at the ground. Slowed time and squeezed space are two ways of telling the identical story. So the faster the twin flies, the shorter her road becomes. The star that sat far across the galaxy creeps closer the harder she pushes. She is not traveling faster than light. The distance she must cover is simply melting away in front of her. Now aim this at the ultimate traveler once more. Light moves at the one speed where the stretch factor blows up to infinity. We already saw what an infinite stretch factor does to time. It freezes the clock. Turn that same infinity loose on distance, and something even more staggering happens to the space that light crosses. The road ahead of a beam of light does more than shrink. It disappears. Point the infinite stretch factor at distance instead of time, and follow it to the end, and you arrive at a conclusion that sounds like a fever dream. For a beam of light, the entire universe in the direction it travels is squeezed down to nothing, not shortened, not compressed a little, flattened to zero length. Remember the pattern. The faster you move, the more the distance ahead collapses. At the speed of light, the collapse becomes total. Every mile in front of the beam, every gulf of empty space, every gap between galaxies, all of it presses down to a single point with no depth at all. For the light, there is no distance to cross, because the distance has ceased to exist. Put this beside what we already learned. For light, no time passes on the journey. And now, for light, no distance separates the start from the finish. Both the time and the space that we see between a star and your eye simply are not there for the photon. It sits at the star and at your eye in the same instant and the same place, with nothing between the two. Imagine the whole cosmos as a thick book, page after page of space stacked between one cover and the other. You, moving slowly through life, must turn every page one at a time to get from front to back. Now imagine slamming the book shut so hard that every page presses into a single sheet, thinner than paper, with no thickness left. Front cover and back cover touch. That is the universe as light meets it, an entire cosmos crushed into one flat instant. This is the deepest reason light never ages. Aging needs a journey. It needs time to pass and space to be crossed. Take away both, and there is no journey left to age through. The photon does not endure a long trip without getting old. It endures no trip at all. Birth and arrival are the same event, at the same point, in the same frozen instant. There is a number that makes this hit home. The light reaching us from the edge of the observable universe has crossed a distance so vast that it would take more than 13 billion years for anything to traverse it at light speed. And the space itself spans tens of billions of miles multiplied over and over beyond counting. To that light, every scrap of that unimaginable distance has shrunk to zero. The farthest reaches of creation and the lens of our telescope press together as neighbors. So the light that shows us the young universe did not truly travel across all that space to reach us. In its own frame, The young universe and our telescope are already touching. The photon is a thread with no length, stitching the most distant past directly onto the present, as if the billions of miles and billions of years were folded flat and pinned into a single point. This picture is beautiful, and it is built on solid math, yet it hides a subtle trap that careful physicists refuse to ignore. We keep speaking of the light's own frame, its own point of view, and there is a quiet, uncomfortable problem lurking inside that phrase, one that forces us to ask whether light truly has a point of view at all. Before we face that trap, it is worth pausing on how tightly the two great effects are bound together, because their partnership reveals the machinery of reality with rare clarity. Time slowing and distance shrinking are not two separate tricks the universe plays. They are one single effect seen from two angles. Watch how they lock arms. Whenever a moving clock runs slow, the space that same mover crosses always shrinks by the exact matching amount. The two never drift apart. If time stretches by a factor of 7, distance squeezes by a factor of 7. If time stretches toward infinity, distance shrinks towards 0. They move together like two ends of a single seesaw, one rising precisely as the other falls. The reason they are chained together comes back to the sacred rule, the fixed speed of light. Picture the universe as an accountant obsessed with one number and one number only. That number is the speed of light, and it must come out the same for every observer, in every rocket, at every speed, no matter what. To protect that number, the accountant is allowed to adjust two things: the amount of time that passes and the amount of distance that must be crossed. Whenever motion threatens to change light's speed, the accountant stretches time and shrinks space in perfect balance to keep the answer fixed. This is why you can never catch light. Speed up to chase it, and your time stretches while your distances shrink, and the two adjustments conspire to leave light racing ahead at the same speed as always. The universe rearranges space and time behind the scenes specifically so that light stays uncatchable. Every rocket, every runner, every particle finds the same wall, held in place by this quiet accounting. Here is a way to feel the trade. Imagine the twin flying toward a distant star. She could describe her trip in two completely different ways, and both would be correct. She could say the distance stayed enormous, but her clock ran so slow that she barely aged crossing it. Or she could say her clock ran normally, but the distance shrank so much that there was hardly any space to cross. Same trip, same arrival, two descriptions that trade time for distance and land on the identical answer. For light, both descriptions are pushed to their limit at once. The clock stops completely, and the distance vanishes completely. And these are simply two ways of saying the same thing. There is no journey. A photon experiences neither the passing of time nor the crossing of space, because the universe has traded both all the way down to 0 to keep light moving at its one eternal speed. This partnership hints at something deeper than either effect alone. Time and space are not the separate, independent stages we always imagined, one for when things happen and one for where. They bend into each other. They trade back and forth. They behave like two faces of a single, unified thing. Physicists gave that unified thing a name, and building it required merging space and time into one fabric. And once you stitch space and time together into a single fabric, you can measure distances across that fabric with a new kind of ruler, one that combines both at once. That ruler holds the final secret of why light's journey always comes out to 0. Space and time, it turns out, are woven from the same cloth, and once you accept that, you can lay a single ruler across the combined fabric. Physicists call this fabric spacetime, and the ruler that measures across it is called the interval. The interval is the true measure of the separation between any two events, and it works nothing like the rulers we use in daily life. An ordinary ruler measures pure distance. The interval measures something richer. To find the separation between two events, say a star flaring and your eye catching its light, the interval blends together the distance in space and the gap in time in one calculation. It weighs how far apart the events are, and how long apart they are, and it fuses them into a single number. Here is the strange heart of it. Space and time do not simply add together in the interval. They fight against each other. The gap in space and the gap in time pull in opposite directions, one working to increase the separation and the other working to cancel it out. For most pairs of events, one side wins and you get a real, solid interval. But for certain special pairs, the two sides balance perfectly and cancel to nothing. Guess which pairs balance to exactly zero? The two events joined by a beam of light. Whenever a photon travels from one event to another, the gap in space and the gap in time cancel completely, and the interval between them comes out to precisely zero. Every path that light takes has an interval of zero along its entire length. Physicists call these light paths null paths, and null simply means zero. This is the deepest, cleanest reason light never ages, stated in the true language of the universe. The interval is what a clock riding along a path would measure. For light, the interval is zero, so the clock reads zero. No time, no separation. The star and your eye, joined by a null path, are separated by exactly nothing in the only measure that space-time truly cares about. Picture two islands far out at sea. On an ordinary map, they sit a great distance apart, and any boat must cross the whole stretch of ocean between them. But the interval draws a different kind of map, one where any two islands connected by a beam of light are marked at zero separation, touching on the chart even while they sit oceans apart in space. The light path is the bridge that measures zero. This idea reshapes the entire night sky one final time. Every star you see is connected to your eye by a null path, an interval of zero. In the truest measure the universe offers, you are not separated from those stars by the vast distances your instruments report. Along the thread of light joining you, the separation is nothing at all. The cosmos is stitched together by countless zero-length threads, each one a beam of light linking a distant event directly to an eye or a lens. So the mystery seems solved. The interval is zero, the clock reads zero, and light never ages. Yet the moment we say a clock rides along the light and reads zero, we have quietly assumed something that may not be allowed. We have assumed you could be that clock. We have assumed light has a place to stand and a moment to call its own. And that assumption hides a crack that runs straight to the foundation. Everything we have said rests on a phrase we keep repeating: the light's own point of view. From the light's frame, time stops. From the light's frame, distance vanishes. It is a powerful way to speak. It is also, according to the very theory that gives us these results, forbidden. Here is the uncomfortable truth. Einstein's theory allows you to describe the world from the point of view of anything that moves slower than light. A person, a planet, a spaceship, even a particle screaming along at 99.99% of light speed all get a valid point of view. The theory hands each of them a working set of rulers and clocks. But the moment you try to build a point of view for light itself, moving at exactly light speed, the whole construction falls apart in your hands. The problem is the stretch factor. To convert into the light's frame, the math asks you to use that factor at exactly the speed of light, where it becomes infinite, and to finish the calculation, you are forced to divide by zero. Division by zero is not a hard problem, it is a meaningless one. The equations do not give a strange answer at light speed. They give no answer at all. They simply stop working. So when we say a clock rides along with the light and reads zero, we are describing something the theory cannot actually deliver. There is no valid frame for a photon. There is no seat to sit in, no window to look out of, no clock that could survive the trip. The light does not experience zero time in the way a bored traveler experiences a short flight. The light has no experience and no frame in which to have one. This might feel like the whole beautiful picture is crumbling. It is not. The picture survives, but it changes character. It stops being a literal story about what a photon feels and becomes a statement about the structure of space-time itself. The interval along a light path really is zero. That is a solid, frame-independent fact. What we cannot do is climb inside the photon and call that zero its personal experience of time. Think of it like the North Pole. Everywhere on Earth, you can ask which direction is north, and you get a clear answer. But stand exactly on the North Pole and ask which way is north, and the question dissolves. Every direction is south. The question has no answer, not because the pole is mysterious, but because north stops meaning anything there. The photon sits at a similar pole in the landscape of speed. Ask what time feels like from its point of view, and the question quietly loses its meaning. This is why careful physicists choose their words with such precision. They will happily tell you the interval along a light path is zero. They will hesitate to tell you a photon experiences no time, because experience requires a point of view, and a point of view is exactly the thing light cannot have. The zero is real, the traveler feeling that zero is a fiction. So why do we keep using that fiction at all? Why do textbooks, teachers, and even great physicists speak of the light's frame when the theory forbids it? Because the fiction, handled carefully, points at something true, and understanding why it works, even though it cannot be real, reveals what light actually is. If the light's point of view is forbidden, why does nearly everyone who explains this reach for it anyway? The answer is that a fiction can be false as a literal picture and still true as a guide. The frozen clock of the photon is exactly this kind of fiction. Wrong if you take it as a real experience. Right if you take it as a signpost pointing toward the interval. Watch how the fiction earns its keep. It gets the destination correct. When someone imagines riding the light and finding the clock stopped, they arrive at a genuine fact that the interval along the light path is zero. The imaginary journey is impossible, yet it lands on real physics. It is a ladder you climb to reach the roof, then kick away once you are standing up top. Physicists lean on tricks like this constantly, because the alternative is drowning in abstraction. The honest, careful statement sounds like this. Along any path a photon takes, the space-time interval is zero, and this is a frame-independent property of null geodesics. That sentence is true and precise, and almost impossible to feel in your gut. The fiction of the frozen clock takes that same truth and makes it vivid enough to grip. As long as you remember it is a signpost and not the territory, it does no harm. Here is the boundary you must respect. The fiction is safe as long as you never treat the photon as a conscious traveler with a real working clock. The moment you do, you can talk yourself into nonsense, imagining the photon bored, or waiting, or aware of arriving. None of that exists. A photon has no clock, no experience, no inner life. What exists is a path through space-time whose interval is zero, and that is a fact about geometry, not about any traveler's feelings. So the correct way to hold this idea is with a kind of double vision. On one hand, the vivid image, light crosses the galaxy in a single frozen instant, aging not at all. On the other hand, the sober fact underneath, there is no valid frame for light, and the frozen instant is a property of the geometry of space-time rather than an experience anyone could have. Both matter. The image gives you intuition. The fact keeps that intuition honest. This double vision also sharpens the original question in a useful way. We began by asking whether light ages. Now we can see the question was slippery from the start, because aging is something a traveler does, and light is not a traveler in the ordinary sense. It has no frame to age within. So, the honest question is not whether the photon feels itself grow old. The honest question is, what actually changes about light as it crosses the cosmos, measured by us, in our frame, where our clocks and rulers work perfectly well. And once you ask it that way, the answer becomes surprising in a whole new direction. Because when we stop trying to sit inside the photon, and instead watch light from the outside, from our own solid vantage point on Earth, we discover that light crossing the universe does change. Something about it shifts on the long journey. It arrives different from how it left. The light that never ages, it turns out, does not arrive untouched. Set aside the impossible view from inside the photon and stand firmly where we actually live, on Earth. watching the sky with real clocks and real instruments. From here, a sharper question comes into focus. Does light change on its long journey across the universe? And the answer splits cleanly in two, because the word aging has been hiding two different meanings all along. The first meaning is the one we have chased so far. It asks whether the light's own internal clock advances, whether the light accumulates time and experience the way your body does. By that measure, the interval along its path is zero, and light is utterly ageless. In this sense, a beam born in the first stars is exactly as young now as the day it was made. Nothing internal has ticked forward. This meaning of aging gives light a clean and total immortality. The second meaning is completely different, and it lives entirely in our frame, not the light's. It asks whether the light itself, the thing we catch and measure, arrives changed. Does it show up carrying less energy? A different color? Some mark of its long passage stamped upon it? This has nothing to do with any clock riding the photon. It is about what we, the observers, actually detect when the ancient light finally lands. These two questions are easy to tangle together, and tangling them causes endless confusion. A person hears that light never ages and pictures light arriving forever unchanged in every way, pristine and identical to the moment it left. That is only half right. The internal clock never advances, yes, but the light we receive from the depths of the cosmos is not identical to the light that set out. Something happened to it on the way. Here is a way to keep the two meanings separate. Imagine a letter carried across an ocean by a courier who somehow never ages a second during the trip. The courier stays forever young, yet the letter itself arrives weathered, its ink faded, its paper worn thin by the long voyage. The courier not aging and the letter arriving changed are two entirely separate facts. Light is both the ageless courier and the weathered letter at once. So what is the weathering? What actually happens to light on a journey across billions of miles of expanding space? The change is real, it is measurable, and we see it every time we look at a distant galaxy. The light arrives stretched. Its waves come in longer and lazier than they left, and its color drifts toward the red end of the rainbow. The farther the light has traveled, the more pronounced the shift. Astronomers can read the distance to a galaxy straight from how deeply its light has reddened. This reddening is one of the most important measurements in all of science. It is how we learn the universe is expanding. It is how we map the cosmos and clock its history. And it seems, at first glance, to look exactly like the light growing tired, losing energy, wearing down across the eons. A kind of aging, after all. So which is it? Is the reddening of ancient light a sign that light does grow old on its journey, contradicting everything we said about its frozen clock? To answer, we have to understand what is really stretching those waves. And the culprit is not the light at all. It is the space the light travels through. Look at the light from a distant galaxy through the right instrument, and you catch it in the act of being weathered. The light arrives redder than it began. Its waves are stretched longer than the waves that left the galaxy. And the farther away the galaxy sits, the deeper the reddening runs. Astronomers gave this effect a name, redshift, and it is written across nearly every distant object in the sky. To see what redshift means, remember what light actually is. Light travels as a wave, a rhythmic ripple with crests and troughs marching along, one after another. The distance between one crest and the next sets the color. Short, tightly packed waves look blue. Longer, more spread out waves look red. Stretch a wave of light, and its color slides toward the red end of the rainbow. Stretch it far enough, and it slips past red into forms of light our eyes cannot even see. Now, here is what we observe. The light from far-off galaxies arrives with its waves stretched longer than they were when they left. A crest that started out close to its neighbor arrives spread wide apart from it. The whole rippling pattern of the light has been pulled out like an accordion opening. And crucially, the amount of stretching grows with distance. Nearby galaxies show a gentle shift, the the most remote galaxies we can find show their light stretched so severely that visible light has been dragged all the way into the invisible. This is not a small or delicate effect. For the most distant galaxies known, light that departed as ordinary visible glow arrives stretched many times over, shifted so far toward the red and beyond that special instruments are needed just to catch it. A wave that set out short and blue reaches us long and deeply red, transformed across the journey. And here is why redshift can look, at first, like aging. A stretched wave of light carries less energy than a tightly packed one. Longer waves mean lower energy, so the light from a distant galaxy arrives not only redder, but weaker, drained of some of the energy it started with. It shows up faint and tired and stripped down, exactly the way you might expect something to arrive after an impossibly long trip. The temptation is to say the light grew old and lost its strength along the way. This is the puzzle we now have to untangle. We spent chapter after chapter establishing that light does not age, that its internal clock is frozen, that no time passes for it at all. Yet here is light arriving, visibly changed, reddened, weakened, seemingly worn by its voyage. The two pictures appear to collide head-on. Either light ages, and its frozen clock was a lie, or light does not age, and this reddening must come from something other than the light growing old. The resolution turns everything around. The light is not what changed. The waves did stretch, the energy did drop, the color did redden, all of that is real and measured. But the cause has nothing to do with the light wearing out or growing tired on the trip. The cause is the space itself. While the light was crossing the cosmos was doing something the light could not resist. The distance the light traveled through was growing. The reddening of distant light comes from a fact so large it is easy to miss. The universe is expanding. Space itself, the empty distance between galaxies, is stretching larger with every passing moment, and light crossing that swelling space gets stretched right along with it. Hold on to what expansion really means, because it is stranger than it sounds. The galaxies are not simply flying apart through space, like debris scattering from an explosion. The space between them is growing. New distance is quietly being created in the gaps between galaxies everywhere, all the time. Two galaxies sitting still relative to their surroundings will still drift apart because the space separating them keeps expanding, inserting more and more distance between them without either one moving an inch. Now, put a wave of light into that expanding space. The light leaves a distant galaxy with its crests packed close together. Then it begins its enormous journey, and while it travels, the very space carrying it swells outward. As space stretches, it drags the light's wave along with it, pulling the crests farther and farther apart. The wave that started tightly packed and blue arrives spread out and red, stretched by the exact amount that space itself grew during the trip. This is the true source of redshift. It is not the light growing tired. It is not the light losing energy to friction or wearing down from the long haul. It is space expanding underneath the wave and hauling it wider as it goes. The farther the light travels, the longer it rides inside expanding space, and the more that space grows during the trip, so the more the wave gets stretched. That is why distant galaxies show deeper redshift. Their light spent more time inside a growing cosmos. Here is a picture that captures it exactly. Imagine drawing a wavy line on a deflated balloon with a marker, a neat little wave with crests close together. Now inflate the balloon. As the rubber stretches, your wavy line stretches with it. The crests slide apart. The wave grows longer, not because you redrew it, but because the surface it sits on expanded beneath it. Light in the expanding universe is that wave, and space is the balloon. The cosmos inflates, and the light stretches along with the fabric it rides. This resolves the collision between our two pictures, and it does so beautifully. The light's internal clock still reads 0. Nothing about the photon aged in the sense of accumulating time, and yet the light we receive is genuinely stretched and reddened because the space it crossed grew larger while it was in transit. Both facts are true at once, and they no longer fight because they describe two entirely different things. One is about the light's frozen interval. The other is about the expansion of the stage the light performs on. So the reddening is not the light growing old, it is the universe growing wide. The light is a faithful record of how much space stretched during its journey, a ruler laid across cosmic time, telling us the expansion in the depth of its color. Yet this raises an obvious and pressing question. When light stretches and its energy drops, that energy has to go somewhere. Energy does not simply vanish. So where does the lost energy of all that reddened light actually go? The answer reaches into one of the strangest bookkeeping problems in all of physics. When light stretches and reddens across the expanding universe, it arrives carrying less energy than it started with. A wave stretched longer is a wave with less energy. So the ancient light reaching us is weaker than the light that first set out. And that leaves us with a genuine mystery, because energy is supposed to be one of the most carefully guarded quantities in all of nature. Energy does not simply disappear. So where did it go? This is one of the strangest bookkeeping problems in physics, and the honest answer surprises almost everyone. The energy the light lost did not go anywhere. It was not handed off to some other object. It was not stored in a hidden account. On the largest scales of the expanding cosmos, that energy is simply gone, and no law of physics is broken in the process. To understand how that can be true, we have to look at why energy is conserved in the first place. The rule that energy can never be created or destroyed rests on a deep and beautiful foundation. Energy stays constant because the laws of physics look the same from one moment to the next. Today's rules match yesterday's rules, match tomorrow's rules. That steadiness in time is what guarantees energy is preserved. Where time behaves the same at every moment, energy is locked in place and cannot vanish. But the universe as a whole does something that quietly breaks this steadiness. It expands. The cosmos is a different size today than it was a billion years ago, and it will be larger still a billion years from now. The stage itself is changing with time, and once the backdrop of reality is stretching, the neat guarantee that kept energy conserved loses its footing. There is no fixed, unchanging cosmic stage for energy to be conserved against. So the energy of the red-shifted light is not paid into any account. It fades out of the ledger entirely, allowed to do so because the expanding universe removes the very rule that would have forced it to be saved. Some describe the light as doing work on the expanding space, pushing outward as it stretches. That picture can help, though the deeper truth is simpler and stranger. In a growing universe, energy on the grandest scale is just not a fixed, conserved quantity the way it is inside your kitchen. Picture a single coin dropped into a piggy bank each day. As long as the bank stays the same bank, every coin is accounted for forever. Now imagine the bank itself slowly dissolving into thin air while the coins sit inside. Ask where a missing coin went, and the question has no good answer because the container that guaranteed the coins would be kept has stopped existing. The expanding universe is the dissolving bank, and the light's lost energy is the coin with nowhere to have gone. This makes the reddening of light even more profound. It is a visible fingerprint of the universe expanding, and a rare place where one of our most trusted laws quietly bends to the scale of the cosmos. The light did not age, and it did not lose its energy to friction or wear. It surrendered energy to the stretching of space, and that energy simply left the books. So the reddening has a clear and settled explanation. Yet before this was understood, another idea competed to explain it. One that claimed light really did wear out on its journey. And for a while, that rival idea looked convincing. To feel how extreme this stretching becomes, follow a single photon from the deep past all the way to a telescope tonight. This photon is born in one of the very first galaxies to light up in the young universe, more than 13 billion years ago, back when the cosmos was a small fraction of its current size and the first stars were only beginning to burn. At the moment of its birth, this photon is vivid. It leaves its galaxy as ordinary visible light, perhaps a clean blue or brilliant white, its waves packed tightly together, brimming with energy. Then it begins the longest journey imaginable, setting out across a universe that will keep expanding beneath it for the entire trip. For over 13 billion years by our clocks, the photon flies, and the whole time, space swells around it. The gap it must cross keeps growing. Its wave, riding inside that swelling space, stretches wider and wider. The tightly packed crests slide apart. The energetic blue light slackens toward red, then past red into the invisible, its waves pulled out longer than a human hair is wide. By the time this photon finally reaches Earth, it is a ghost of what it was. Its once vivid, visible light has been stretched so severely that it now arrives as faint infrared or even weaker radiation, invisible to your eyes, detectable only by specialized instruments cooled to guard against their own heat. The photon comes in tired, drained of most of its energy, reddened almost beyond recognition. The letter, weathered by its ocean crossing, arrives with its ink nearly washed away. This is exactly what the great space telescopes are built to catch. The most powerful of them are tuned specifically to see this deeply reddened light, because it is the only kind that survives the journey from the earliest galaxies. When astronomers point these instruments at the emptiest looking patches of sky and stare for hours, faint smudges emerge. And those smudges are galaxies as they appeared in the universe's first chapter, revealed only by their exhausted, stretched out glow. And now hold both truths in your mind at once, because this is the heart of the whole story. That photon, so battered and reddened by our reckoning, aged not one instant on its own clock. In its own frozen frame, the interval of its entire 13 billion year journey is zero. The blazing young galaxy that made it and the sensor that finally caught it are, along the photon's null path, the same event. It left and it arrived in a single, timeless flash. So the light is ancient and untouched at the same time, depending entirely on which meaning of aging you use. By our clocks, it is the oldest traveler imaginable, weathered by more than 13 billion years of expanding space. By its own measure, it is newborn, unaged. Its clock still stopped at zero. The reddening records the age of its journey through space, while its frozen interval records that, for the light, no journey happened at all. This double nature, ancient and ageless together, is one of the most beautiful facts in science. But it took decades to sort out, because a competing explanation for the reddening refused to die quietly. That rival claimed the light truly did grow old and tired on the way. To see why it failed, we have to meet it. Before scientists agreed that space itself was expanding, a bold and tempting alternative tried to explain why distant galaxies glow red. The idea was simple, almost intuitive. Maybe light really does grow tired on its long journey. Maybe, over billions of miles, a beam of light slowly loses energy, wears down, and reddens, worn out by the sheer length of the trip. This became known as the tired light idea. It arrived early, proposed by a clever astronomer named Fritz Zwicky in the late 1920s, right as the strange reddening of distant galaxies was first being measured. The appeal was obvious. In everyday life, everything that travels a long way loses energy. A rolling ball slows, a thrown stone falls, a shout fades with distance. So the notion that light might likewise tire out and redden across cosmic distances felt natural and reasonable. The tired light idea offered a clean prediction. If light simply drained energy steadily as it traveled, then the farther a galaxy sat from us, the longer its light would have journeyed, and the more energy it would have lost. That means more distant galaxies would appear more deeply reddened, and this matches what we actually see. Distant galaxies really are more reddened than nearby ones. On that single test, tired light and the expanding universe made the same prediction. Both explained the basic pattern, that farther means redder. For a while, this left the two ideas locked in a genuine contest. One said space was growing and stretching the light. The other said the light was wearing out as it crossed static, unchanging space. Both fit the headline fact, so the argument could not be settled by redshift alone. To imagine the tired light picture, think of a long-distance runner. At the start of a race, the runner is fast and strong, full of energy. Mile after mile, the runner tires, slows, and fades. Tired light imagined every photon as a runner like this, setting out vigorous and blue, then flagging across the eons until it staggered in weak and red. The reddening was the light gasping for breath at the end of an impossibly long race. It was an elegant idea, and for a time it was a serious contender defended by serious scientists. If it had been correct, our whole picture of the cosmos would look completely different. There would be no expanding universe. The redshift would be a sign of light aging rather than space growing, and much of what we believe about cosmic history would collapse. So, which explanation is right? Does light genuinely tire and lose energy as it crosses space, aging after all? Or does space expand and stretch the light, while the light itself stays ageless? To break the tie, scientists needed a test where the two ideas made different predictions, a place where tired light and the expanding universe would finally disagree. They found one, and the test was ingenious, using distant stellar explosions as clocks ticking across the cosmos. When the results came in, they pointed unmistakably in one direction, and the tired light idea met the evidence that would finish it. The test that settled the argument used one of the most reliable events in the universe as a stopwatch. Certain exploding stars, a type of supernova, brighten and fade in a very predictable pattern. They flare up, reach a peak, then dim away over a set number of days, following almost the same schedule every time. Because that schedule is so consistent, these explosions act like standard clocks scattered across the cosmos, each one ticking out its brightening and fading on a known timetable. Now comes the clever part. The expanding universe and the tired light idea make sharply different predictions about these cosmic clocks, and the difference is something we can measure. This is the crack where the two ideas finally split apart. Think it through. In an expanding universe, distant events do not only redden, they also appear to unfold in slow motion. Because space stretches while the light travels, the light from the beginning of a distant explosion and the light from its end gets spread farther apart in time by the very same stretching that reddens the waves. So an explosion far away should not only look redder, it should look slower, its rise and fall stretched out over a longer span than the same explosion nearby. The tired light idea makes no such prediction. If light simply drains energy over distance while space stays fixed, then a distant explosion would redden, but it would still tick at its normal speed. Its brightening and fading would take the usual number of days, the same as a nearby one. Tired light reddens the clock without slowing it. Expanding space reddens the clock and slows it down together. So, astronomers went hunting for distant supernovae and timed them with great care. They watched explosions far across the universe brighten and fade, and they measured exactly how long each one took. Then they compared those durations to nearby explosions ticking at normal speed. The distant explosions ran slow, every one of them. A supernova whose reddening placed it far across the cosmos took visibly longer to brighten and fade than an identical explosion nearby. And the amount of slowing matched the amount of reddening precisely, exactly as an expanding universe demands. The more reddened the explosion, the more its clock was stretched, tick for tick, in perfect agreement with space itself expanding. This was the blow tired light could not survive. There is no way for a beam that merely lost energy to also stretch time across a distant explosion. Slowed clocks in the depths of space are the signature of expanding space, and they appear exactly where and how the expanding universe predicts. The reddening was never light growing old. It was space growing wide, dragging both the color and the timing of distant events along with it. To picture it, imagine a song recorded far away and played back to you across the cosmos. Tired light would play the song at normal speed, but shift every note lower in pitch. Expanding Space plays the song slowed down and lower, the whole melody dragged out and deepened together. The universe hands us the slowed, deepened version, and that is only possible if space itself is stretching. So, light does not tire on its journey. Its frozen clock stands. Yet one more piece of evidence sealed the case even more firmly, and it came from the oldest light in all of existence. Light that has been traveling since almost the beginning of time and still glows as a flawless rainbow. The final blow to the tired light idea came from a glow that fills the entire sky, in every direction, all the time. It is the oldest light in the universe, and the shape of its color carries a message that tired light could never fake. To understand why, we first need to talk about the shape of a rainbow. When something glows purely from its heat, its light spreads across many colors in a very particular pattern. A hot coal, a glowing filament, the surface of a star, all of them emit light in a smooth, characteristic spread of colors that physicists call a thermal glow. This spread has a precise mathematical shape, a gentle curve rising to a peak at one color and falling away on either side. That exact curve is the unmistakable fingerprint of light born from pure heat, and it depends only on temperature. Now, here is the crucial fact. If light tired out unevenly as it traveled, losing different amounts of energy at different colors, that beautiful thermal curve would get distorted. The smooth shape would develop bumps and dips, warped by the uneven draining of energy across the spectrum. Tired light, wearing down the beam as it crossed billions of miles, would leave the oldest light with a mangled, twisted rainbow instead of a clean one. So, scientists measured the oldest light with extraordinary care. This ancient glow has been traveling since the universe was a newborn, more than 13 billion years, longer than any other light in existence. If any light should show the wear of a tired journey, it is this one. Its rainbow should be the most distorted of all. Instead, its rainbow is essentially perfect. When precise instruments measured the spread of colors in this ancient glow, they found the smoothest thermal curve ever recorded in nature. A flawless heat glow with no bumps, no dips, no distortion. The oldest light in the universe carries a perfectly clean rainbow, exactly the shape it would have if nothing had drained or damaged it unevenly on the way. This is impossible under tired light. A beam wearing out over billions of years would arrive with its rainbow warped. A flawless rainbow means the light was not tired at all. It was simply stretched uniformly by the expansion of space, which reddens every color together and preserves the smooth shape of the curve. Expanding space slides the whole rainbow toward red without bending it. Tired light would have bent it. The rainbow stayed clean, so tired light was wrong. Picture a photograph of a sunset. Tired light is like the photo fading unevenly, some colors bleaching faster than others, leaving the image blotchy and ruined. Expanding space is like gently enlarging the whole photograph, every color shifting together while the picture stays sharp and true. The oldest light in the universe arrives as an enlarged, unblemished picture, not a blotchy, ruined one. With that, the case closed completely. Light does not age or tire on its journey. Its frozen clock holds, and the reddening we see is the universe stretching, stamped uniformly across every ancient beam. But this flawless ancient glow is more than a piece of evidence. It is a relic, a survivor from the dawn of everything, and it deserves a closer look on its own. That flawless ancient glow has a story worth telling on its own, because it is the single oldest thing any of us will ever encounter. It is light left over from the infancy of the universe, and it is still washing over the earth this very moment, faint and cold and everywhere. Rewind to the young cosmos, a few 100,000 years after its birth. Back then, the entire universe was a hot, dense, glowing fog. It was so hot and so crowded that light could not travel freely. Every beam was immediately scattered by the thick soup of particles filling all of space, trapped, unable to fly in a straight line. The whole universe was opaque, a glowing wall of fog in every direction. Then the universe expanded and cooled, and at a certain moment, it dropped below a critical temperature. The fog cleared. The particles combined into the first stable atoms, and all at once space became transparent. In that instant, the light that had been trapped for ages was suddenly set free to fly in straight lines across the cosmos. And it has been flying ever since, for more than 13 billion years, without being stopped. That freed light is what we now catch as the oldest glow in the universe. It set out as a warm, bright radiance from a fog cooling to the temperature of a stovetop, but it has been traveling through expanding space for over 13 billion years, and all that expansion has stretched it enormously. Its waves, once short and warm, are now stretched into faint, cold radiation far below the reach of your eyes, a whisper of light chilled to nearly the coldest temperature possible. You are bathed in this ancient glow constantly. It arrives from every direction in the sky at once, a uniform hum of radiation left over from creation. Old television sets, tuned between channels, would catch a tiny fraction of their static from this very glow, meaning a sliver of that snowy screen was light from the newborn universe. The dawn of everything has been quietly raining down on us the whole time. And here again is the double truth that defines this whole story. This light is more than 13 billion years old by our clocks, the most ancient traveler imaginable, stretched and cooled by the entire history of cosmic expansion. Yet, on its own frozen clock, it has aged by exactly nothing. The moment it was set free, and the moment it lands on a detector, today are, along its null path, the same instant. It is at once the oldest light alive, and light that has not aged a single tick. So this glow is a fossil and a newborn together. It carries a perfect snapshot of the universe as it looked when it first turned transparent, frozen and delivered across billions of years without aging on the way. Reading it has taught us more about the origin of the cosmos than almost anything else we have ever measured. But the sheer endurance of this light raises a question we have circled without facing directly. This glow has survived, intact, for more than 13 billion years. And that forces us to ask something we have quietly assumed all along. Can light ever simply die on its own? We have watched light cross billions of miles without aging and arrive from the dawn of the universe still glowing. This raises a question we have taken for granted without ever testing. We have assumed light just keeps going, forever, until something absorbs it. But is that actually true? Left entirely alone in empty space, does a beam of light travel on without end, or does it eventually give out? Think about how unusual that assumption is. Everything else in the universe seems to run down. Stars burn out, mountains erode, particles decay. Even the most stable atoms will, given enough time, eventually crumble. Wear and decay appear to be the universal fate of everything. Yet we have quietly assumed that light alone escapes this destiny, sailing on unchanged for as long as the universe lasts. And the evidence so far backs that assumption in dramatic fashion. The oldest glow in the universe has been traveling for more than 13 billion years, and it arrived intact, its rainbow flawless, its light still here to be measured. Whatever else time does to the cosmos, it has not managed to snuff out that ancient light across the whole age of the universe. Light seems, so far, essentially immortal. But essentially immortal is a careful phrase, and the gap between essentially and truly immortal hides real physics. To say light lasts forever with certainty, we would need to know that a photon, left completely alone, can never fall apart on its own. And whether it can turns out to depend on one specific property of light, a property we usually take for granted, the fact that light has no mass. This is where the question sharpens. Everything we have said about light rests on it being massless. Massless is why light moves at exactly the speed of light. Massless is why its clock is frozen. And massless might also be why it can never die. because in the deep rules of physics, whether a particle can decay into other particles depends on whether it has mass to begin with. Picture the difference between a settled boulder and a boulder balanced on a knife edge. A truly massless particle is like a boulder resting on flat ground, with nowhere lower to roll, no way to fall apart into something else. Give it even a trace of mass, and suddenly there might be a lower place for it to tumble to, a lighter set of particles it could crumble into. Mass is what opens the door to decay. No mass, and the door may be sealed forever. So the immortality of light, the thing we have quietly assumed all along, comes down to a question physicists genuinely investigate. Is light perfectly massless, sealing the door to decay and making it truly eternal? Or does light carry the tiniest whisper of mass, cracking that door open, giving it a lifetime after all, however enormous? This is a real open question in physics, and scientists have hunted hard for the answer. What they found is one of the most staggering numbers in all of science: a lifetime for light so vast it makes the age of the universe look like an eye blink. To reach it, we first have to ask what would happen if light did carry a sliver of mass. For everything we have said, light is massless, moving at the one speed reserved for weightless things. But how sure are we? What if light carries the faintest possible sliver of mass, so tiny it has slipped past every measurement so far? That single possibility changes light's fate, because a particle with even a whisper of weight can, in principle, fall apart. Here is the rule that governs whether anything can decay. A particle can only break apart into other particles if those pieces together weigh less than the original. Nature allows a heavier thing to crumble into lighter things, releasing the leftover energy. It forbids a thing from crumbling into pieces that weigh more than itself. So, the whole question of whether a particle can decay comes down to whether there is a lighter set of pieces for it to become. Now, apply this to light. If light is perfectly massless, then it is already as light as anything can possibly be. There is nothing lighter for it to decay into. The door to decay is not just closed, it never existed. A massless photon is stable forever by the deepest logic of physics, because there is no lower place for it to fall. But if light carries even the tiniest mass, the situation flips. Suddenly the photon weighs something, however little, and there might exist even lighter particles it could break apart into. The door to decay creaks open. A photon with a whisper of weight becomes, in principle, a thing that could one day fall apart into lighter fragments, releasing its sliver of energy and ceasing to be light. So which is it? Scientists have measured with ferocious precision whether light has any mass at all, and every experiment agrees on the same thing. If light has any mass, it is fantastically, almost unbelievably small. The limit they have placed on it is staggering. Light must weigh less than a tiny fraction of a billionth of the mass of a single electron, and the electron is already among the lightest particles known. If light has weight at all, it is a whisper of a whisper of a whisper. Picture trying to weigh a single grain of pollen using a scale built to weigh mountains. Now imagine that even that absurd scale detected nothing, and you needed a scale 1,000,000,000,000 times more delicate, and still it read 0. That is roughly the situation with the mass of light. We have weighed it with the most sensitive instruments ever devised, and the reading keeps coming back as either nothing at all or so close to nothing that we cannot tell the difference. So light is either perfectly massless, and therefore immortal, or it carries a mass so absurdly small that it sits right at the edge of what we can ever hope to measure. Both possibilities are still technically open, and that leaves a door, however narrow, for light to have a lifetime after all, which raises the obvious question. If light does carry that faintest imaginable sliver of mass, if the door to decay is cracked open by a hair, then how long would light actually live? Scientists ran the numbers for even the heaviest weight light is allowed to have. The answer they got is one of the most jaw-dropping figures in all of science. Suppose light does carry the tiniest sliver of mass that experiments still allow, cracking open the door to decay. How long would a beam of light survive before falling apart? Scientists worked this out, using the very heaviest weight light is permitted to have. The answer is a number so enormous it strains the mind. Even if light carries the largest mass we could possibly have missed, a single photon would live, on average, for around a billion years before decaying. Write that out and it is a 1 followed by 18 zeros. A billion years. That is the shortest possible lifetime light could have, and only if it sits at the very heaviest edge of what experiments allow. If light is lighter than that, as it almost certainly is, it lives far longer still. To feel how vast a billion years is, compare it to the age of the universe. The entire cosmos, from its birth to this moment, has existed for a little under 14 billion years. A billion years is roughly 100 million times longer than that. If you lined up the whole history of the universe end to end, over and over, you would need to repeat it about 100 million times just to reach a single photon's shortest possible lifetime. Put another way, in the entire time the universe has existed, light has lived through less than 100 millionth of even its shortest allowed lifespan. Every photon from the dawn of the cosmos, all the ancient glow we catch today, has barely begun its life. It is not old at all by its own natural clock of decay. It is freshly born, with an ocean of time still ahead of it, even in the gloomiest case where light carries a whisper of weight. And remember, this billion year figure is the pessimistic answer, the shortest life light could possibly have. It assumes light sits at the absolute heaviest edge of what we have failed to rule out. Every measurement suggests light is far lighter than that, most likely perfectly massless, which would push its lifetime not just to a billion years, but to forever. Picture a candle that has burned for the entire history of the universe, since the first instant after the beginning, through the birth of every star and galaxy, up to this very night. Now imagine that candle has not even burned through the first thin sliver at its tip, that its full length still stretches ahead, enough to outlast 100 million more universes. That is the lifespan of light, even in the worst case. A candle that has scarcely started, so whether light is truly immortal or merely lives a billion years, the practical answer is the same. Across the entire span of cosmic history, light effectively does not die. It keeps traveling, keeps shining, keeps carrying its frozen instant across the ages, functionally eternal on every timescale that has ever mattered. But there is a final twist buried in that gigantic number, and it braids together everything we have learned. That billion year lifetime is measured on our clocks, the clocks of observers watching light from the outside. And light, as we know by now, keeps a very different clock of its own. Here is the twist hidden inside that colossal number, and it ties the whole story into a single knot. That billion year lifetime for light is measured on our clocks, by us, watching from the outside. But light does not live on our clock. Light lives on its own frozen clock, the one that reads 0. And on that clock, the story becomes stranger than any number can hold. Recall the deepest fact we uncovered. For light, no time passes at all. The interval along its path is 0. Its internal clock is frozen solid, stopped forever at the instant of its birth. So when we say light might decay after a billion years, we are speaking entirely in our own time, the time of observers who watch light fly past. From the light's own frozen frame, that billion years collapses, like every other span, down to nothing. Think about what this means. In our frame, a photon that carries a whisper of mass might survive for a billion years and then fall apart. But those billion years, stretched across the future of the cosmos by our reckoning, are pressed by the light's frozen clock into a single instant. On the light's own measure, its entire immense lifetime is one timeless flash, from birth to decay, with nothing in between. So even the death of light, if it ever comes, would be, for the light, simultaneous with its birth. The photon would not experience a long life followed by decay. It would experience nothing. its beginning and its end welded together in the same zero instant, the way its emission and absorption always are. Whether light lives forever or lives a billion years, its own clock cannot tell the difference, because both amount to the same frozen zero. This is the final unity of the whole idea. Everything about light points to the same place. Its speed is fixed because it has no mass. Its clock is frozen because it moves at that speed. Its journeys take no time because its interval is zero. And now even its lifetime, however vast, shrinks on its own clock to the same eternal instant. From the light's perspective, if we may borrow that forbidden fiction one last time, its entire existence, whether brief or infinite, is a single unaging flash. Picture two versions of the same photon. One is watched by us, and we see it born in a distant galaxy, fly for a billion years, and finally, perhaps, decay in the far future of the universe. The other is the photon itself, for which birth and flight and decay are all one instant, no duration, no aging, no passage of any kind. Both descriptions are of the exact same light. They simply keep different clocks, and the light's clock never moves. So the question we began with, whether light ages, now has an answer that runs all the way to the bottom. In our time, light endures across billions and billions of years, functionally deathless. In its own time, it experiences no duration at all, not even its own potential death. By every measure that touches the light itself, it never grows old, because for light, there is no old to grow into. Yet we, watching from the outside, get something extraordinary out of this arrangement. Because light does not age or die on any timescale that matters, it becomes something no other traveler could ever be, the one witness present across the entire history of the universe. Because light effectively never ages or dies, it becomes something utterly unique in all of nature, the single witness that has been present through the entire history of the universe and survived to tell us about it. Nothing else endures the way light does. And that endurance turns light into the messenger that carries the whole story of the cosmos to our eyes. Consider what this means for how we know anything at all about the universe beyond Earth. Every fact we have ever learned about distant stars, galaxies, and the deep past arrived on a beam of light. We have never touched a star. We have never visited another galaxy. Everything we know about the cosmos came riding in on light, because light is the one thing that can cross those unimaginable distances and arrive with its message intact, unaged, undecayed. And here is the profound part. Because light carries a frozen snapshot from the moment it was born, and because it survives across billions of years without wearing out, looking into space is the same as looking into the past. The farther out we look, the older the light we catch, and the earlier the era it shows us. Light lets us see the universe at every age of its life at once, simply by looking at different distances. Point a telescope at a nearby star, and you see light a few years old, showing that star in the recent past. Point it at a distant galaxy, and you catch light millions of years old, revealing that galaxy long before humans existed. Point it at the very edge of what we can see, and you receive light from the dawn of everything, showing the universe as a newborn, in a single sweep across the sky. Light lays out the entire history of the cosmos for us to read. No other messenger could do this. If light aged, its ancient snapshots would be corrupted, warped by the passage of time, useless as records of the past. If light decayed quickly, the oldest light would have vanished long ago, and the early universe would be lost to us forever, unreachable and unknowable. It is precisely because light never ages and never dies that the deep past remains visible, preserved perfectly in beams that have been flying since the beginning. Picture a library where every book is a beam of light, and none of the books ever crumble or fade, no matter how old. The most ancient volumes, written at the birth of the universe, sit on the shelves as crisp and readable as the day they were made. We walk into that library every time we look up, and we read the oldest chapters of reality in light that has carried them, unchanged, across all of time. The universe wrote its own history in a medium that never decays. So light is far more than a thing that happens not to age. Its agelessness is the reason we can know the cosmos at all. It is the incorruptible record, the witness that never forgets, the courier that carries the deep past into the present without losing a single detail across billions of years. And this transforms the simple act of looking at the night sky into something staggering. Because every point of light above you is one of those ancient, unaging messengers, and together they turn the sky into a window onto all of time at once. Step outside once more and look up, now knowing everything we have uncovered. That quiet sprinkle of stars is no longer just a pretty view. It is a collection of frozen instants gathered from across the entire history of the universe, each one delivered to your eye by a messenger that never aged on the way. The night sky is a museum of time, and every point of light is an exhibit from a different age. Look at one star, and you are seeing light that left it years or centuries ago, a snapshot of that star frozen at the moment the light departed. Look at another, farther off, and its light is older still, showing it as it was long before the first stars you looked at even sent their beams. Every star you see is displaying itself to you at a different moment in the past. All of those moments arriving together in your single upward glance. Turn to the faint smudges between the stars, the distant galaxies, and the depth of time grows staggering. Their light has been traveling for millions of years, so you are seeing them as they were before humans walked the earth. Frozen images of galaxies that may have completely transformed in the ages since. Some of them may not even exist anymore in their current form. You are looking at ghosts, perfect portraits of a past that the light carried to you unchanged. And every one of these images is a frozen instant in the most literal sense. Each beam left its source in a single moment and, on its own clock, never aged a tick on the way to you. So the light truly is a preserved slice of that moment, sealed the instant it departed and opened only now as it lands in your eye. You are not seeing these stars and galaxies as they are. You are seeing the exact instant they released their light, held in perfect stillness across all the years between. This means your single glance at the sky assembles moments from wildly different times into one picture. The light hitting your eye right now left its many sources across a vast spread of history, some a few years ago, some millions, some over 13 billion. Yet all of it arrives at your eye in the same instant, layering countless frozen moments from across cosmic history into a single scene. Your one look is a collage of all of time. Picture a single photograph that somehow contains snapshots taken across every era of history at once. A face from last year beside a scene from the age of dinosaurs beside a glimpse of the world's very first morning, all blended into one image. That impossible photograph is exactly what the night sky is. Light, by never aging, gathers moments from every chapter of the universe and arranges them together above your head. So the sky is not a view of the present. It is a view of all times, woven into one, made possible entirely by light's refusal to age. Each unaging beam preserves its moment perfectly and hands it to you across the gulf of years, turning a simple upward glance into a look across the whole span of existence. And behind every one of those frozen instants lies the single strangest fact of all, the one that has haunted this entire journey. For the light that carried each of those moments to you, no journey ever happened. There was no crossing, no waiting, no span of years at all. We arrive at the strangest fact of all, the one that has shadowed every chapter of this story. For the light that has traveled billions of years to reach you, the journey never took any time, not almost none. None. Birth and arrival for the light are the same instant. The entire voyage, however vast it looks to us, was a single ageless flash with no inside and no duration. Hold the two pictures together one final time, because their collision is the whole wonder of this story. In our frame, a beam of light from the edge of the universe crossed an ocean of space for more than 13 billion years, stretched and reddened by expanding space the whole way, an epic voyage across nearly the entire history of the cosmos. In the light's own frame, that same beam left its source and arrived at your eye in one instant, having crossed a distance that shrank to zero, aging not a single moment. Both of these are true. They are two descriptions of the exact same beam of light, and neither one is wrong. Ours is the view from the outside, where time passes and distance is real, and the journey is immense. The light's is the view from the impossible seat we are forbidden to occupy, where time is frozen and distance is nothing and there is no journey at all. The universe holds both truths at once, without contradiction, because time and space themselves bend to keep light moving at its one eternal speed. This is why light never ages, stated in its purest form. Aging requires a journey through time. For light, there is no journey. The start and the finish are welded together in a single zero instant, with no span between them for age to accumulate. A photon does not endure a long trip and stay young. It endures no trip at all. Every beam that reaches you is exactly as young as the instant it was born, because for the light, that instant of birth and this instant of arrival are the same instant. So the star and your eye, separated by centuries and unimaginable distance in our world, touch directly in the world of the light. The distant galaxy and the telescope, 13 billion years apart by our clocks, are pressed together as one event along the light's frozen path. Every beam is a bridge of zero length and zero duration, stitching the deep past directly onto the present moment, as though no gap ever existed between them. Picture the whole history of the universe as an immense scroll unrolled across billions of years, with the birth of a distant galaxy near one end and your eye near the other. In our view, light must travel the entire length of that scroll to connect the two. In the light's view, the scroll is folded so that those 2 points touch, and the light passes between them with nothing in between. The vast scroll of cosmic history collapses, for the light, into a single fold where beginning and end press together. This is the final answer to the question we began with. Light may never age, no matter how far it travels, because for light, there is no distance and no time to age across. Its whole existence, its every journey, and even its potential death are one unaging instant, held frozen forever at the speed that binds space and time together. The messenger from the deep past is, in its own timeless frame, always exactly newborn, arriving in the very moment it was made. You're right, I stopped at 30. Here are the final 3. Everything in this story has quietly been teaching us a single lesson, and it is worth naming outright because it is the foundation the whole mystery rests on. Time and space are not two separate things. They are two faces of one deeper reality, and light is the thread that reveals their unity most clearly of all. We are used to treating time and space as completely different kinds of thing. Space is where things sit, time is when things happen. A mile and a minute feel like they belong to different worlds, measured by different tools, with nothing in common. For all of human history, that separation seemed obvious and unbreakable. Space was the stage, and time was the clock ticking beside it, each independent of the other. Einstein's work tore that separation down. We saw it happen piece by piece, all through this story. When you move fast, time stretches and space shrinks together, always in perfect balance, one trading against the other to keep light speed fixed. That trade only makes sense if time and space are the same kind of stuff, able to convert into each other the way ice and water are the same substance in different forms. They bend into one another because they were never truly separate to begin with. Light is the purest proof of this unity. For a beam of light, time collapses to zero and distance collapses to zero at the very same moment, welded together by the single fact that light moves at the one speed reality permits. The freezing of the light's clock and the vanishing of the light's road are not two coincidences. They are one event seen from two angles, because time and space are one fabric and light travels along the seam where the two meet and cancel. Think of it like a coin spinning so fast you cannot tell heads from tails. In everyday life, time and space look like two separate sides of that coin, and we only ever notice one at a moment. But push toward the speed of light, and the spin blurs the two together until you can no longer say where one ends and the other begins. Light lives permanently in that blur, at the speed where time and space merge into a single, seamless thing, and the distinction between when and where simply dissolves. This is why light behaves so unlike anything else in the universe. It is not a strange object moving through space and time. It is a phenomenon riding along the very place where space and time fuse into one, the seam that stitches the whole fabric together. Its frozen clock and its vanished distance are not oddities to be explained away. They are the clearest window we have into the true, unified nature of reality underneath the everyday illusion of separate space and time. So the agelessness of light is not just a quirk of one kind of particle, it is a direct glimpse of the deepest structure of the universe, the merging of space and time into a single fabric, made visible in the one thing that travels along their meeting line. To understand why light never ages is to catch the cosmos in the act of showing you what it is truly made of. And that glimpse leaves us with one last question, the one that turns this entire story back toward you. If light carries a frozen instant across all of time, and if that instant touches your eye every time you look up, then what does it mean that you are the endpoint of every one of those timeless journeys? Every beam of ancient light we have followed across this whole story shares one final destination, and it is worth facing directly. That destination is you, the eye that catches the starlight, the endpoint where each timeless journey finally comes to rest. And that makes you a stranger and more remarkable part of the cosmos than you might ever have guessed. Consider what actually happens when starlight lands in your eye. A photon born on the surface of a distant star, flung into space across years or centuries, crossing a gulf so vast that no human vehicle could ever hope to span it, ends its entire existence the instant it strikes the back of your eye and is absorbed. For that photon, its birth on the star and its death in your eye are the same event, the two ends of a journey that took no time at all. You are the place where its frozen instant finally opens and delivers its message. This means something intimate about the simple act of seeing. When you look at a star, a piece of that star, a real particle of light forged in its blazing surface, physically reaches across space and time and touches you. Along the light's frozen path, the star's surface and your eye are pressed directly together as one event. In the truest measure the universe offers, you are not separated from that star by unimaginable distance. You are in direct contact with it, connected by a thread of light that measures zero. So every time you look up, you are not a passive observer staring at faraway things. You are the completion of countless journeys, the endpoint where light from across the entire history of the universe arrives to finish its trip. The dawn of the cosmos, the birth of distant galaxies, the fire of ancient stars, all of it reaches out across billions of years and lands. At last, in you, you are where the deep past finally arrives. And here is the quiet wonder of it. The atoms of your eye, the very cells that catch the light, are themselves made of matter forged inside stars that lived and died long ago. So when starlight lands in your eye, the universe is, in a real sense, looking at itself. Star stuff, built into a living eye, catching light from other stars across the gulf of time. The cosmos folds back on itself in that moment, and you are the fold, the place where light completes its timeless journey and the universe becomes aware of its own light. Picture the whole night sky as countless threads of light, each one stretching from a distant star or galaxy across all of space and time, and each one ending in a single point at the back of your eye. You are the knot where all those threads come together, the destination of every ageless beam pouring in from every direction and every era at once. All of that frozen time, all of that vanished distance, converges on you. So the light that never ages is not some abstract curiosity happening far away in the void. It ends in you. Every time you look up, you are the shore that all those timeless journeys wash up on, the end point of light that has crossed the universe without aging a single instant to reach exactly here, exactly now, exactly you. And that leaves just one thing left to say, the thought that gathers this entire journey into its final, simplest form. We have crossed the whole strange landscape of light, from frozen clocks to vanished distances, from reddened ancient glow to a lifetime beyond imagining. And it all gathers, in the end, into one simple, staggering truth. To the light itself, its entire billion-year voyage was a single, ageless flash, nothing more. One timeless instant, from beginning to end. Gather what we have learned into that single image. Light moves at the one speed the universe permits, forced there by having no mass. At that speed, its clock stops completely, frozen at zero. At that speed, the distance ahead of it collapses to nothing. Its journey across the cosmos, however vast to us, takes no time and covers no distance in its own reckoning. Emission and absorption, birth and arrival, and even its far-off possible death, all press together into one instant with no duration at all. The whole of light's existence is a single flash that never ages. This is why the star you looked at, all the way back at the start, sends you light that is at once ancient and newborn. By our clocks, that light is centuries, or millions or billions of years old, weathered by expanding space, a relic from the deep past. By its own frozen clock, it is exactly as young as the instant it was made, unaged, untouched, arriving in the very moment of its birth. Both are true. The light is a courier who never ages, carrying a letter that took no time to deliver across a distance that, for the courier, was never there. And this is not a small or isolated fact about one kind of particle. It is a direct view of the deepest structure of reality, the place where time and space merge into a single fabric, made visible in the one thing that rides along their seam. To understand why light never ages is to see the universe reveal what it is truly made of underneath the everyday illusion of separate space and separate time. The frozen instant of light is a window straight into the bones of the cosmos. So the next time you step outside and look up, you will know what you are truly seeing. Not just points of light, but ageless messengers, each one carrying a frozen instant from somewhere across the vast history of the universe, each one ending its timeless journey in your eye. You will be standing at the shore where all of cosmic time washes up at once, catching light that crossed the universe, without aging a single moment to reach you. Picture it one last time. A photon leaves a star at the dawn of the cosmos. It crosses an ocean of space and an age of time so immense we can barely hold the numbers in our minds. And then, tonight, it lands softly in your eye and ends. To you, it traveled for billions of years. To it, no time passed at all. Its birth in the ancient fire and its death in your eye are the same instant, the same event, a single unaging flash spanning all of creation and lasting no time whatsoever. That is why light may never age, no matter how far it travels. For light, there is no far, there is no journey, there is no time. There is only the flash, frozen and eternal, forever, exactly as young as the moment it was born, arriving always in the instant of its making. The universe crosses itself in a single, timeless step, and every beam of light is that step, taken again and again, across all of space and all of time, and aging never at all.